This is the second of two lectures on nuclear properties and models. The focus is going to be on applications to understanding nucleosynthesis, that is the origin of the elements and the frequency with which various elements are found, and some properties of radioactivity. We'll talk about fusion and fission in particular. I have several slides in this presentation that go back to the previous lecture, and they're intended to remind you of things that we learned in the previous lecture. I'm not going to go over them again today, but during class I will actually discuss these slides in a little bit more detail. So I'll go back through this as a review in the regular class. This is also going to be review. This slide is going to be review as well, so I'm not going to discuss it now. This one is review. Liquid drop model is a review slide, so I will discuss it during the regular class. And this will also be discussed during the regular class. The Fermi gas model is also something that's going to be discussed during the regular class, so I'm not going to spend time on it now. And there's one more slide on the Fermi gas model, and this is an illustration of that, which I will discuss during the regular class. Fermi gas model can be extended, improved by changing some details, and that's called the shell model, and I will talk about that during the regular class. So now we come to the material that I'm going to focus on in this lecture, which has to do with the actual nuclear stability and transitions or reactions that occur in order to go from a less stable nucleus to a more stable nucleus. Here's a chart that I got from Brookhaven National Laboratory, a government laboratory, that gives an overview of how we think about the stability of nuclei. There are a few things to keep in mind in interpreting a chart like this. Well, first we need the scales. On this axis is the number of protons, so the element would be determined by moving along this axis here. And if you look very carefully in here, you'll see that the element names are actually given for each number of protons, atomic number here. And on this axis is the number of neutrons in the nucleus. And we see here that the stable isotopes, the stable nuclei, sort of sit along a diagonal here, but it turns out that they're not right on the diagonal of the number of protons equal to the number of neutrons, because if I go out to 80 here, 80 neutrons, and 80 protons here, then we see that the number of protons equal to the number of neutrons sits well above this valley of stability. Nuclei that appear to be more stable have more neutrons than they have protons. And the underlying reason for this is that protons repel one another, and there's a Coulomb energy associated with having more than one proton in a nucleus, and they want to be as far away from one another as possible. There is a strong force, but overall the strong force is between adjacent nucleons, and the electromagnetic force can extend across the entire nucleus, and in fact is much stronger than the strong force between two nucleons that are on opposite sides of a nucleus. Of course, the problem is actually quantum mechanical, and we're talking about probability densities, but the overall idea of protons on average wanting to be further apart, and the only way that they can be further apart is to have neutrons sitting with some probability density between them. So it will be energetically or favorable as far as the Coulomb force is concerned to put more neutrons than protons. However, neutrons in themselves are unstable. They will decay to protons by the emission of a proton, an electron, and an electron neutrino, antineutrino, in order to conserve the number of leptons in the problem. So if we have too many neutrons, that is, we're sitting off to this side here, too many neutrons, then ultimately the neutrons will simply decay to protons and electrons, and the nucleus is actually going to decay. If I have too few neutrons, that would be on this side here, then the protons are not adequately buffered. So there is an optimal line here, which does correspond to about 8 million electron volts per nucleon binding energy. The binding energy is highest for iron and cobalt, which sit somewhere around here, binding energy per nucleon, and the binding energy per nucleon is quite a bit lower out here, and as a result, these nuclei will actually energetically break down into nuclei in this size range in order to gain energy per nucleon, and binding energy per nucleon. So in this chart here, we've got number of protons on this axis, number of neutrons on this axis, value of stability along the middle here, which corresponds to what we've been showing you in previous lectures. And all of the yellow isotopes here are unstable. They will decay until they reach some point along the valley of stability. We'll look at some of the decay schemes in a moment, but if an isotope sits somewhere out here, then it will decay toward the valley of stability by either electron capture or by positron emission. Sodium-22 decays by positron emission, for example. All right, so it will move toward stability. If you have too many neutrons, then those neutrons are going to decay by proton and electron emission, which takes an isotope which is here and moves it diagonally toward the valley of stability. The other major decay mode is alpha emission, which is shown over here. If I have too many protons, that is Coulomb repulsion is too great, and too many neutrons, that is that the neutrons themselves are inherently unstable, it can be energetically favorable for the nucleus to decay by emitting an alpha particle. An alpha particle is 2 protons and 2 neutrons. We'll talk about that in more detail later on. I have discussed on the previous slide, as I talked over things, what are some of the reasons that nuclei are unstable, and I just want to make sure that those are laid out here. Number 1, Coulomb repulsion between the protons requires extra neutrons in order to space out the protons. The strong force is just between neighbors, and if I have a lot of protons, there are protons that are not nearest neighbors that are repelling one another. And then we have the problem that neutrons themselves are inherently unstable. They decay in about 11 minutes into a proton and an electron and a neutrino. And they will do that in the nucleus as long as there's an actual lower energy state for the proton to go into after the repulsion is accounted for. I'll show you something about that on the next slide. Here's a figure from the previous lecture, which applies to tellurium-125, an isotope of tellurium. And these are approximate Fermi gas energy levels that were deduced by solving the Schrödinger equation for a quantum well of a certain depth. The depth for the quantum well of neutrons is deeper than the depth for a quantum well of protons that holds this many protons and neutrons together, right? Because the protons repel one another. Neutrons and protons are different particles, so each of them form their own set of levels that are filled. And in this particular case, for tellurium 125, we have put in the appropriate number of neutrons and the appropriate number of protons. And the Fermi level for neutrons is not very different in energy from the Fermi level for protons. And if there were such a situation that a neutron could decay into a proton and go into a lower energy level, then that's a decay mode that could actually occur. It looks as though that could happen here because it looks as though there's a state here that's a little bit lower than that one in energy. However, when we convert a neutron to a proton, we actually change the potential well, making it more repulsive, and everything here shifts up. So we'd have to recalculate and compare this energy diagram with the extra proton to see whether it's energetically preferred for the neutron to actually decay or not. So here are some combination of processes that start with elements that are unstable, and then those elements decay, and either by alpha decay, which moves us diagonally down 2 by 2, or beta decay, which moves us diagonally down by 1, but because it's an electron that we're losing, the direction is in the positive neutron direction. This plot here has got the neutron number on the y-axis and the proton number on the x-axis. You'll find that different textbooks and different sources will switch the axes on you, so be careful about looking at this. So in this case, beta decay takes an electron out, which increases the proton number. Right? So back to this. Here's a potential pathway. Plutonium-239 decays by alpha to uranium-235, which decays by alpha to thorium-231, and then by beta to Pennsylvanium, I think, 231, alpha, and so on. Okay. The lifetimes for the various processes depend upon the energetics of the nucleus and a process that I'm going to talk about in a few minutes that has to do with alpha decay. Usually beta decays are more rapid than alpha decays. You see up here, for example, that this alpha decay is 710 million years, whereas the beta decay is 25 hours. All right. So you won't find a lot of thorium-231 around because it rapidly decays to Pennsylvanium 231. This is a set of possible decays that it could occur that go from plutonium 239 to lead, and lead is stable. right? Same here. Here's another possibility starting with thorium-232, decays via alpha and beta processes, ultimately ending up again with a stable isotope, lead, right? Most of these heavier atoms cannot be found naturally and have to be created in a reactor or an accelerator. So the actual analysis of what goes on is that we can think of our protons and neutrons as being in a quantum well. And when they're inside the quantum well, what forms the quantum well is the strong interaction with the neighbors. So now if you want to take a proton out, for example, the moment that it moves away from the neighbors, it experiences a Coulomb repulsion, which will drive it away. But maybe the important thing here is that that creates a potential barrier for a charged particle, a positively charged particle, to leave the nucleus. It is bound in here by strong force. As soon as it tries to move away, then there's this potential barrier due to the Coulomb interaction. So first of all, there's a problem in alpha decay in that we have to get 2 neutrons and 2 protons together in order for them to travel out together, right? So there's a low probability of actually getting those particles to form a quasi-helium nucleus inside of another nucleus, and then that conglomeration of nucleons has to make it out through the barrier. If we make an estimate of the probability that an alpha particle will get excited over the barrier, it turns out that we'd need extremely high energies, and the probability of that happening is extremely low. And so the process that explains how this can actually happen is tunneling of the alpha particle from its internal state through the Coulomb barrier and then out so that it is free. Okay, so it's got a tunnel at this energy from here to there so that it's now can be a free wave function again. And once it's out, it will accelerate away. But it has to, first of all, have some energy. This would normally be the Fermi energy. And then it's got to tunnel through this barrier. And we can make some estimations of the effective tunneling probability through the barrier by taking the barrier and breaking it up into a whole bunch of little rectangular barriers. In the Coulomb barrier region, the wave function has a form that looks like this, right? It decays exponentially, and then because it's a radial wave function, it has a 1/r term, right? And that tunneling length here is related to the height of the barrier, the energy of the particle that's tunneling through, and the mass of the particle. So the probability that the alpha makes it out through the barrier depends upon the thickness of the barrier and the height of the barrier. And when we plug all of this in, then we can come up with an estimate of the probability that the particle makes it out. It is this low tunneling probability that leads to long lifetimes for alpha emitters. We'll now turn our attention to some very important processes that are called nuclear fusion and nuclear fission. Currently, nuclear fission is a very important energy source Earlier in the summer, you had a presentation from nuclear engineers about the importance of fission. And fusion is an extremely important energy source over which we do not have sufficient control at this point, but it is the source of energy in our sun and most stars. So, and all stars, let me take that back. So it's an important process for us to understand. We have a lot of information in the tables and in the data in the textbook right now that tell us about the nuclei, and we can begin to figure out what the processes are that give rise to energy release in fusion and fission. The information that we want to look at is the binding energy per nucleon, and then there will be some limitations which we're going to discuss when we get to particle physics with respect to what is permitted. The primary law that we're going to look at right now with respect to what is permitted is the question of whether a reaction is energetically favorable or not. And then when we get to particle physics, we'll talk a little bit about other conservation laws, and two that we're going to mention here is that it is required that the number of baryons, that is the number of protons and neutrons, be conserved in a nuclear reaction or decay. And the second is the number of leptons, that is electrons, electron neutrinos, and other specific neutrinos, are those conserved in the reaction. So let's start now to talk about energy sources that have to do with the sun and processes that give rise to the elements and the abundance of elements that we see around us. So the first stage in a fusion process that occurs in the sun, in the fusion process that occurs in the sun, is the fusion of two protons. So the protons have got to be energetic enough to actually smash into one another. And for a brief period, they will come together and interact via the strong force. But the Coulomb force wants to drive them apart. And so if this reaction occurs where we put two protons together, and if those two protons decay rapidly enough into a proton and a neutron, so that's called a deuteron, and that's what I've got here, all right, into a deuteron, plus the release of a positron. So some of the positive charge is carried away. And then we need neutrinos in order to balance things out. We'll talk about that later on. That releases about 1.4 million electron volts. Can it happen easily? No. Those two positively charged protons do not want to approach to one another. They have to be forced together. Right? What would be the next stage? Because actually what we know is that in the sun, one of the primary elements that is being created is helium. So let's see how we can actually get helium out of these processes. So now I've got my deuterons, and so that's a neutron and a proton. And if they collide with sufficient energy with another proton, then that will form helium-3, a neutron and two protons. Again, in order to get them to come together, I have to overcome a Coulomb barrier. So it's going to take energy from the surrounding plasma in order to do that. That is, these two things have to come in with sufficient kinetic energy to get close enough to one another and overcome the Coulomb barrier. If they do, that process releases 5.5 million electron volts, a lot of energy. And then if I can bring two helium-3s together, then they will form a helium-4, an alpha nucleus, an alpha particle, plus two protons are released. And that process releases 13 million electron volts. Once again, getting this to occur is difficult because we're bringing two doubly positively charged nuclei together, and there's a Coulomb barrier that keeps them from coming together. Therefore, the gas that these are in has to be very hot. That process releases, or rather, the total processes that lead to the alpha particle and two protons, right, release nearly 27 million electron volts, or an energy release in this process of 6.7 million electron volts per nucleon. Right, that's beginning to move us up that stability curve, the binding per nucleon. It's lower than the peak, which is about 8.8 million electron volts per nucleon, but we have gained a huge amount of energy by putting all of these protons initially together with the decay into neutrons by beta emission. So this process now is called the proton-proton chain. This occurs in the sun. If we try to make an estimate of what kind of temperatures we need in order, for example, to get two protons to fuse, we could very simply ask, well, how much kinetic energy do we need in order to get the two protons close enough to actually fuse? Well, we should try to get them within about a femtometer of one another, because that's the range of the strong force. If we work out what the Coulomb energy would be, it turns out that it's about 1 million electron volts to get them that close together. That temperature, if I have to have kinetic energies of order 1 million electron volts, then that temperature corresponds to about 10 to the 10th Kelvin. It actually turns out that the interior of the sun is closer to 10 to the 7th to 10 to the 8th Kelvin. So that means that this process with the two protons getting together actually occurs even though they don't have enough energy to get within a femtometer of one another. How does it happen? It's actually been worked out and demonstrated that the process that permits it to happen is quantum tunneling. Just like the alpha particle tunneling out, the protons tunnel in order to get close enough to have a strong force. The world around us has heavier nuclei than just helium. The sun is heavy enough to gravitationally hold helium, but helium actually leaves the surface of the Earth. And there are a lot of heavier elements that make up the world around us and make up us, right? So we need further nucleosynthesis processes. And the most favorable processes include taking those alpha particles that we formed and reacting them with one another, bashing them into one another at high temperature. All right. Now we're in 10 to the 7th to 10 to the 8th Kelvin in order for this process to occur. So a cooler star won't have a lot of helium burning, but a hotter star will. And we can take two alpha particles, put them together, and get beryllium-8. And then we could collide beryllium-8 with helium, or rather, we're talking about nuclei, all right, with the alpha particle, and get carbon. And helium plus carbon can make oxygen, and helium plus oxygen gives us neon. So we can get up to, we can continue, but it turns out that as we increase the charge on the nuclei, the Coulomb barrier gets bigger and bigger, and the tunneling probability decreases exponentially as the barrier gets higher. So the rate at which these processes occur, even at a particular temperature, is going to decrease as we move to heavier nuclei. So helium burning is somewhat limited in what it can produce, and there are processes that can give rise to let's say, higher probability, higher abundances of slightly heavier nuclei. So, but in a typical star, this process can occur, and so a typical star, towards the end of its life at least, can produce beryllium, carbon, oxygen, neon, for example. But the abundances of these elements is going to go down as we move to heavier and heavier nuclei. Although, by the way, the nuclei in this range are more stable, they are approaching 8 million electron volts per nucleon. And so the probability that a beryllium atom nucleus is going to react in order to form something heavier can be higher. So we might deplete the beryllium, for example. All right, in order to create some other elements that aren't just in the helium cycle here, we need to do things like collide a proton with carbon. That forms nitrogen-13, and then nitrogen-13 will decay into carbon-13. Then a proton incident on carbon-13 can form nitrogen-14. So now we've got elements that aren't multiples of 4. All right. So we need to collide protons into some of the products here in order to make other elements. Those 3 cycles that I just mentioned, the proton-proton cycle, the helium cycle, and the carbon cycle, can explain the relative abundances of the elements. I mentioned that beryllium is depleted by the formation of heavier elements. All right, so we see that beryllium actually is depleted. Beryllium-8 isn't stable, and but that once we get to the stable nuclei, we find, for example, that the amount of carbon that we find is much greater than the amount of nitrogen, total carbon greater than total nitrogen. This is only about a factor of 5 or so. But then the amount of oxygen is higher because that's one of the helium cycle elements. So carbon plus helium yields oxygen. And then you can see 4 higher, we end up with neon. 4 higher, we end up with magnesium. So adding helium does this. And we see that the probability of finding those nuclei, the relative abundances in the universe of these nuclei, is greater. All right? And that's because it's part of the helium cycle. But as we get heavier, that probability goes down. And then in order to form the elements in between, we have the carbon cycle, for example, and the collision of protons with nucleons, right? By the way, do note that this is a logarithmic scale here. So we can see large relative abundances of even Z elements. Those are going to be the helium multiples, and small for the odds, right? The lighter elements aren't formed in the reactions that we've got up here. So lithium, beryllium, and boron aren't formed. So those are not produced, right? So we don't see many of those. And the relatively large abundance of iron, you see iron is way up here, is because that's actually the end product of the fusion cycles, because iron has got the most energy stored in the binding energy per nucleon for these stable materials, for any material. Here's a second overall summary of the periodic table, which is based now on the probable origin of the elements. What we've got in here, all right, is that the formation of hydrogen in helium is best explained by a Big Bang nucleosynthesis. Hydrogen formed in the Big Bang itself, protons, and helium being produced as well. All right. But then in stars, the hydrogen can burn. Burn is an improper word. Can fuse in order to form helium, and that's a second mechanism. And you see in here that we've got low mass stars that can form helium. There's a little bit in there. Okay. Lithium is formed in low mass stars. Beryllium, oddly, by beryllium, the stable isotope, by cosmic ray fission. All right. Then carbon and nitrogen formed in stars. Right. The heavier elements are most likely or best explained by exploding massive stars. Right. So all these yellow elements in here. The gray elements here are formed by exploding white dwarfs. So we have to have sufficient energy in order to actually create the fusion to actually make these elements. But fusion will work up to iron, and then after that, we can momentarily fuse something, and then it will fission in order to produce other things in here. So our common elements, like the very lightest elements, are only formed in let's say standard type stars. Low mass and intermediate mass stars will form these green and yellow elements in here. And then in order to get anything heavier, we have to have supernova. When heavier elements are formed by fusion or other similar processes, and by man-made processes, then we can ask how it is that, what is the process by which those elements decay into more stable nuclei. Here's an example for californium. It has too many protons and neutrons to be stable. So this is man-made, actually. If you work through and you ask, all right, if I'm undergo a beta decay, that is, that I'm going to increase the number of protons, for example. A neutron might decay to a proton because the neutrons are unstable. We find out that that's energetically unfavorable. Alpha decay for these very heavy nuclei has a very large Coulomb barrier, and therefore alpha decay process is a very slow process, very long-lived, all right? And if we look, we find that these heavy nuclei frequently decay by just breaking into two lighter nuclei. They just separate into two more stable nuclei, gaining the energy of binding. So californium can decay into xenon and ruthenium and neutrons, but this particular breakdown isn't a law, all right? There's just some probability that it's going to decay into one thing or another. This is the probability distribution of the fission products from, in this case, californium, which is the process that I had here. And what I've got here is the breakdown of californium 254, right, into two components. Xenon 140, so we'll look over here, 140 is around there, and ruthenium 110, which is around here, right? So that's a very probable pathway. If you look at this, corresponds to the maxima, but other products can come out. That is, the californium can decay into something with an atomic mass of 100, and another thing then has got to add up properly to about 154 or so. So it's less probable, but it can happen, that californium can break into a variety of possible fission products. The reason that it breaks up is that the binding energy per nucleus is greater for the lighter nuclei until we get to iron. Iron has got the greatest binding energy per nucleon, and so fission will occur until you reach iron, or can occur until you reach iron, and then below that, iron will not fission any longer. Iron is the most stable nucleus. Fission, man-made fission at least, is most easily induced by neutron capture. So you take a nucleus which is that might decay by alpha emission, for example, that's gone a long lifetime, and if you can collide it with a neutron, then you can form a nucleus that has a higher probability of decaying by fission. And so the cross-section for uranium-235 fission by neutrons depends upon the energy of the neutrons, and you can see that very low energy neutrons have a very large probability of being captured by U-235 and then causing fission to occur. And if we've got energetic neutrons, then they are much less probable to actually induce fission. So in a nuclear reactor, we'll typically add materials in order to slow the neutrons down in order to increase the cross-section for fission to occur. A typical fission sequence would be this, that a neutron is incident on uranium-235. Uranium-235 fissions into products. In this case, an example product is rubidium and cesium, all right, which then decays to strontium and cesium, all right. So that comes out. Those processes there now release neutrons. The fission process itself, the initial process, releases 2 neutrons, which can then be slowed down because they're coming out energetically. They get slowed down and they can get captured by another U-235, more fission, or by U-238, which leads to decay processes. But if we want a sustained energetic reaction, then we want these neutrons to be captured by uranium-235, which causes more fissions, releasing more neutrons, which then react with more uranium-235. Fast neutrons could easily escape and not interact with any uranium-235. So there is actually a critical amount of uranium-235 that you've got to have in order for a sustained fission reaction to occur. We'll talk more in class about fission reactions and the ramifications of this, but this covers the primary content for today. I will talk about this in class, and the next slide I will talk about in class.